Hello and welcome to Gaffey's Grinds. My name is Jesse Gaffey and I am a Leaving Cert chemistry teacher. And in this channel, we take concepts from the Leaving Cert chemistry course, we break them down, try and explain them as simply as possible, and give you guys some practice to do. Now, it's this practice that makes our channel different from other channels, in that other channels will probably have videos which are shorter than these, but they will probably just talk through the videos, maybe explain things a little bit, but they don't necessarily give you opportunity to practice and master the content. So that's why this channel is a little bit different. And it also means the videos are a little bit longer, but I think you will learn the information really, really well. You will master the content. This is video one of a new series on radioactivity. So in these next coming videos, we're going to discuss radioactivity, and we're going to start at the beginning and we're going to build up in small little pieces. Couple of warnings before we begin. I ask you always to close any unnecessary tabs that you have open on your computer or tablet, especially any social media, because that's just going to distract you and it's going to make it much harder for you guys to learn. Also, the whole channel is based around practice and doing retrieval practice of information to make sure you guys actually are learning what we're talking about. And if you're not going to do the practice, if you're just going to sit and listen and wait for me to tell you the answers, then you're not going to learn anything basically by watching a video. So you're wasting your time here. Now, if you're here, I'm guessing you want to learn. So make sure you do the task to the best of your ability. So the story of radioactivity, it begins with this man. This man is called Henry. He's a French scientist called Henry Becquerel. I have to check the spelling of this because it's French and I don't really speak French. So Henry Becquerel is this man's name. Now, this man he studied rocks for a living. So that's what his job was, to study rocks. He studied rocks. And this is in the 1800s time. So science was still pretty, junior, still pretty immature, if you like. We didn't have this understanding of things that we do now. So studying rocks doesn't sound like a job that you might have now, even though we still have geologists. But this man in particular was what we call a mineralogist, a mineralologist, mineralogist. And basically that means he studied minerals. Ologist means mineralogist. He studied minerals. Okay, so he studied rocks, and specifically he was looking at the types of compounds that you find in rocks. He was also an avid photographer. So photography was relatively new at the time, and photos were black and white. And it worked like this. You got a piece of like cardboardy paper type stuff, and it was brushed with a compound called silver halide. Silver halide. And silver halide is a white compound. White. So you took your piece of cardboard or paper and you brushed it with this chemical called silver halide. And it was white until some light shined on it. So when some light shined on this silver halide, it turned it black. So essentially what you would do is you would take your camera and you would take a photograph, and the cameras would all have a flash on them, and that would send light out. The light would hit off the object that you were photographing and come back into your camera. And wherever the light hit, the shape of the light that reflected back would hit your photograph plate, as we call it. This was called a photographic plate. And say you were taking a picture of a tree, the light would come back in the shape of the tree, and it would cause the photographic plate to go black in all the places where the light hit. So where the light didn't hit, the plate would stay white. And that's how you created a photograph, a black and white photograph. So the light would be in the shape of the tree because it bounced back off the tree. And everywhere else, light didn't hit. It would stay white. This here was called a photographic plate. Plate. So Becquerel was a mineralogist and he was also a photographer. So he had these photographic plates lying around that he would use to take photographs. And by pure accident, he discovered that he was basically storing some of his photographic plates in a drawer. So this was a drawer in his desk. So his photographic plates were over here in the corner. So this is a stack of photographic plates. Or it might have been just one, I'm not sure exactly, but that doesn't really matter. Photographic plates. So we had the photographic plates in the corner, and he also kept some of his rock collection in the same drawer. And what he discovered by accident was actually that he noticed that where he was keeping sometimes when he kept the rocks in the drawer with the photographic plate, what would end up happening is that the plate would go black in a kind of spot closest to where the rocks were being stored. So when a photographic plate goes black like this, we say it's exposed because it's exposed to light. So the photographic plate was becoming exposed on the side that was near the rock. So this here was a rock. Okay, and again, he figured out, or what his suggestion was, that the rock must be giving off some kind. It obviously isn't giving off light. It's not lighting up the drawer, but it's obviously giving off some kind of invisible emissions. It's giving off some kind of energy, some kind of invisible emissions. Now, years later, or it wasn't years later actually, they already knew that these rocks, this particular rock, contained the element uranium. Contained the element uranium. So what Becquerel concluded is that some atoms must give out emissions, invisible emissions that we can't see. So atoms give out emissions. Now this wouldn't happen with every type of rock that he left in the drawer. It would only happen with specific types, and he figured out that this happened when he kept rocks with uranium. This here, this invisible emissions, became known by the name radiation. Radiation was the invisible emissions, so that were being emitted from the rock. So they are invisible emissions given out from the rock. So what Becquerel had actually discovered was what we call radioactivity. So Becquerel had discovered radioactivity. Now I'm going to give you a definition for this later on. I'm not just going to jump in and give it to you now because I want to show you some other things before I give you the definition for radioactivity. But we know that Becquerel was the person to discover radioactivity. Now, I just want to show you, these are some actual pictures of his photographic plates. So these are actual images of the photographic plates from Becquerel's drawer. So you can see these areas here, which are exposed, and the white areas around these are unexposed areas that have not been exposed to energy of some kind. So light is a form of energy or energy transfer. So radiation is another thing or another form of energy that can cause exposure on a photographic plate. So this is exposed and the white area is unexposed. So the exposed area was close to the rock and the unexposed area was sheltered from the rock. All right, we're going to stop at this point and we're going to do some practice questions and make sure that you guys have learned what we're talking about. So I'm going to get you guys to open up a copy or wherever you're going to do the questions, and I want you to pause the video and try and answer these questions the best you can. Try and use full sentences where possible. You will notice that number 1, 2, and 3 are retrieval questions from previous topics. So these are topics that you would have, or you definitely should have studied before doing this. They're pretty straightforward recall questions about atomic structure that I definitely think you guys would have done before you do radioactivity. So pause the video and answer the questions now. Okay, so you should only be listening. You should only be hearing my voice if you have paused and done the questions. If you are just going to sit and wait for me to talk about the answers, then you are not going to learn anything. So just know that. Okay, so state the particles in the atom which carry charge. So in an atom, which particles carry charge? Well, that would be the protons and electrons. Protons and electrons are the atoms with charge. If I asked you, oh yeah, so next question then. State two types of charge. Well, two types of charge are positive charges and negative charges. So positive, and we have positive are protons, by the way. Okay, so I'm spelling that wrong, sorry. We have positive charge. I'm going to put that under protons because positive goes with the protons. And we can also have negative charge, and negative charge goes with the electrons. So that's why I'm keeping it in that order. Do like charges attract or repel? Now, like charges, that means if I've got two positives or two negatives, those are like charges. Two positives or two negatives, those are like charges. Do they attract or repel? Well, if I put two positive charges together, they will repel. And if I put two negative charges together, they will repel. Repel is the opposite of attract. If things attract, they kind of get sucked or attracted together. They get stuck together. And if they repel, then they push apart. So again, all of that is recall stuff I would expect you to know from doing atomic structure. Number 4, who was Henry Becquerel? So who was he? Well, he was a French mineralogist. He was a French scientist, you can call him, but his specific job was he was a mineralogist. He'd studied minerals in rocks. He's a French mineralogist. And what did Henry Becquerel discover? He discovered radioactivity. Radioactivity. This is 4 and this was 5. So well done. If you got those right, do make a point of correcting them. You should either be ticking your answers or you should be fixing them. So if you have them right, tick them with a red pen. And if you are a different color than you wrote in, and if you didn't have them right, then make changes to your answer and fix them now. All right, on to a little bit more information. Right, to help us understand what radioactivity is, we're going to have to look at these. These are 3 atoms of carbon. We've got carbon 12, we've got carbon 13, and we've got carbon 14. Now, if you've studied atomic structure already, then you guys should know these 3 different versions of atoms of carbon. What name are these known by? So how I want you to answer this question is I want you to speak your answer out to the screen. Don't worry, nobody can hear you. I know it's a bit weird, but I'm going to ask you to do this at times during these videos. So do speak your answer out loud to the screen. So on 3, 1, 2, 3. What do we call these? Okay, I hope that you said isotopes. We call these isotopes. So these are 3 isotopes of carbon. Now, why are they isotopes? What is an isotope? Well, an isotope or isotopes are atoms of the same element, so they're all carbon, that have different numbers of neutrons. So take a look down here. Carbon 12 has 6 protons and 6 neutrons. Now, the 6 protons thing, that's what makes it carbon. You'll notice that all of them have 6 protons. If they did not have 6 protons, then they would not be carbon. So they all have 6 protons, but look here, they have different numbers of neutrons. And that gives them different masses because carbon 12 has a mass of 12 because it's got 6 protons and 6 neutrons. Carbon 13 has a mass of 13 because it's got 6 protons and 1 extra neutron. It's got 7 neutrons. Carbon 14 has extra mass again. It's got 6 protons but 8 neutrons. So these are 3 isotopes of carbon. Now, this is the key to understanding radioactivity. Most atomic nuclei, most atoms that exist naturally are what we call stable. Now, what does stable mean? Well, stable means that the protons and the neutrons are securely stuck together. There's the exact right amount of energy in there to keep them stuck together, and they will pretty much stay stuck together forever and ever. Now, in the world, there exist different percentages of each of these isotopes of carbon. Most of the carbon in the world is carbon 12, and carbon 12 is stable. So the atoms are stable like this with 6 protons and 6 neutrons. This is the right amount. This is a balanced amount of protons and neutrons, and there's not too much energy there. So this nucleus is stable. It doesn't want to break up. Carbon 13 is also stable. So this configuration with 6 protons and 7 neutrons is also stable. So these two are what we call stable isotopes of carbon, carbon 12 and carbon 13. But some nuclei, and again, it's not all elements, only some elements have these unstable nuclei. So basically, an unstable nuclei is where you've got an unbalanced amount of protons and neutrons, and the atom has too much energy to stay together. So there's kind of a lot of turmoil in the nucleus. There's a lot of vibrations. There's too much energy. The protons and neutrons are jostling and fighting for spaces, and it's just not a stable configuration. So it's what we call an unstable nuclei. Unstable. And what does that mean? What's the problem with unstable? Well, what happens is when you've got an unstable nuclei, eventually the nucleus is going to break up at some point. And when it does this, it's going to give out a particle. And in the next video, we'll see what type of particles it could give out. It's going to give out a particle. In other words, a piece of the nucleus is going to break off. So you're going to release a particle, and that extra energy that was in there, that was too much energy, is also going to be given out. It's also going to be released. Now, obviously, if you give out a particle, like some protons or neutrons, then what's left behind is going to be a changed nucleus. It's not going to be carbon-14 anymore. So we'll give out particles, and it'll keep firing out pieces until it reaches a state that it's stable. So it's all about trying to become a stable nucleus. Now, again, all of these three isotopes exist in the world naturally. They occur naturally. But carbon-14 doesn't last forever because it's going to break up eventually until it becomes a stable nucleus. Okay, so that's what we're talking about here, is an unstable nucleus. What we call this is we call this a radioisotope. A radioisotope. And that is this guy here, is a radioisotope. So as a definition, a radioisotope is an isotope with, an unstable nucleus. So a radioisotope is an isotope with an unstable nucleus. Carbon-14 is a radioisotope. Carbon-12 and carbon-13 are not radioisotopes. They're just normal isotopes or standard stable isotopes. A radioisotope is the unstable one, carbon-14. With that in mind, now we can kind of have a better definition for radioactivity. I told you earlier I would give you a definition for it eventually. Now that we can actually understand what's going on, it's probably easier for me to define it. Well, what we're talking about is, now it doesn't take any special reaction to happen for radioactivity to occur. It's just completely random. So once every so often, a radioisotope is going to release a particle. It's what we call spontaneous. It's not planned. It's not predictable. We just know that the atom is unstable, and at some random point, it's going to spontaneously break up, which that just means it's random. It's not planned. There's not any mad event for it to happen. It's not like there's a little button that you press and it breaks down. It's spontaneous. It can happen at any point. Spontaneous breakup, because the nucleus does break up, it releases pieces. Breakup of unstable nuclei with the emission just means to release, emission of radiation. So radiation is like what the rocks were giving out. So uranium must be another radioactive substance. So there must be some isotopes of uranium that give out, that are radioactive, and they give out emission. And emission is this invisible, like particles or energy that's given out by unstable atoms. We call this spontaneous breakup of unstable nuclei with the emission of radiation. We call this radioactivity. Now, I would suggest at this stage that you pause the video and take that down, them definitions. Okay, so you should only be playing the video if you've made a note of your definitions. And then it might be an idea, if you're interested in having a nice way, a diagram, a visual of it, if you take that down as well. Again, if you're interested in having notes that explain radioactivity. It might be an easier way for you to remember it if you remember the 3 different diagrams of isotopes. Okay, so you should only be watching the video now if you're ready to go and answer questions. I want you to cover them notes, put them away. You shouldn't be looking at them while you do your practice. Practice is all about retrieving from memory. Forget about copying. If you're copying answers down from your notes, you're learning absolutely nothing. Okay, so put that away. You can come back to it at another point if you need to read over it again. But let's see if you can do it without the notes now. Okay, so what I have here is I have a second set of questions for you. So questions 1 to 7. Okay, I want you to pause the video and answer the questions now. All right, you should only be watching the video if you have paused and answered these questions using full sentences. I'm going to show you the answers now, and I'm going to give you an opportunity to make corrections to them. So here comes the answers. Okay, so I'm just going to move my head out of the way. There we go. So pause the video, make any corrections you need to now using a red pen. All right, so you should have pretty much exactly what I have written. You might have worded some of the things a little bit differently, but you're going to have certain key parts in there. Okay, so do read through my answers, compare them to your own, and see, would you, now that you've seen what the correct answer is, would you think you would get all the marks for your answers? Are they good enough? Okay, all right. That's it, guys, for the first video. I'll see you in the next one. It's good to have you join. If you found this easy to follow, if you found it useful, you think other students might benefit from watching it, do give the video a like, leave a comment down below about, maybe tell me what you liked about it or what you didn't like about it. And if you would like me to do any videos on other topics, do let me know in the comments so I can get a head start, start making them for you. Okay, see you in the next video.